this short video is to add more clarity to windowing functions because I believe there were some confusions regarding that. So let's get started. Well, we saw that the input sinusoid to the ADC must be of this form, that is cos of 2 pi times m by n times n. Right? So this should be the signal after sampling, where m and n must be co-prime. Right? And as an example, we chose this signal, that is cos of 2 pi times 201 by 1024 times n. And of course, this is a signal that is periodic with a period of 1024 samples. Right? So if we capture 1024 samples of this signal, that is, if we truncate this signal for a total of 1024 samples, it might look something like this. So let us say these are the samples I get. Okay, so this is going to be a sinusoid, right? And since the frequency is 201 by 1024, within these 1024 samples, it is going to complete 201 cycles, right? So let us say I get something like this. Okay, and okay, maybe a lot better. Okay, so let's say this is my sample at n equal to 0. Let's say this is my last sample at 1023. Fine. So let me mark these boundaries also. Right. So now, if I try to capture, that is, if I try to perform a 1024 point DFT on this data, so what the DFT will do is the following. It will assume that the signal we are dealing with is a periodic signal. So it will take this data, that is these 1024 samples, and it will repeat it on either sides, and it will do it forever, right? And forms a periodic repetition of this signal, okay? And the DFT will find the spectrum of this periodic signal, right? So now if we try to form the repetition, that is form a periodic repetition, by taking the signal and pasting it to the right, what will happen? So let's say this is my 1024 sample. So this 1024 sample here will be same as the sample at n equal to 0, right? Because you are going to form the repetition. So I'll have the repetition like this. Right? So similarly to the left side, I'll have the same repetition. So this sample at n equal to 1023 will come here to the left. So I'll have the signal to be like this, right? And this is a smooth sinusoidal signal, right? Okay, and there is no problem with this. But now, in practice, let us say the frequency has a slight error. So the resulting sample signal becomes cos of 2 pi times 201.01 by 1024 n. So now let us say we try to capture the same 1024 samples for this signal. How will it look like? Well, since the frequency is 201.01 by 1024, it will complete 201.01 cycles, right? So the samples might look something like this. So let's say we get this sinusoid, and then it will continue. And what might happen is that it will complete 201 cycles here, right? So let me draw it here. So let's say it completes 201 cycles at this point. It will keep going, right? Because it is going to finish more than 201 cycles, right? So the waveform might look something like this. Okay, so yeah. And now if we try to take the 1024 point DFT, what will happen? This data will get repeated on either sides, right? So the sample at this instant, this instant 1024, that is this time instant, will be same as the sample at n equal to 0. So the sample will be like this, right? And I'll form the periodic repetition like this. Okay, so similarly here, the sample to the left of n equal to 0 will be same as this sample, right? So I'll have something like this. Okay. So now we can clearly see that at the boundaries, that is at these points, there is a sudden jump in the signal. Okay. And these jumps result in the spectral leakage. That's what we saw here, right? And also adds a flat portion to the spectrum. So now let us see why these sudden jumps here add a flat portion to the spectrum. So for this purpose, let's try to model this signal. Okay, so one simple way of thinking about this signal is that we can say that here to this signal is a smooth sinusoidal signal to which we are adding some kind of an error. Okay, so we can think of it as some error signal getting added to an otherwise smooth sinusoid. Okay, and how will that error signal look like? So let us say this is my axis n. We notice that this error, that is these jumps, occur at the boundaries of the window, right? So we'll have this error occurring at n equal to 0. This is 1024, at 2048, and so on, right? So let me extend the axis further. So at every multiples of 1024, we'll have this error getting added. And how will this error look like? Well, we know that the error is going to be maximum at these boundaries, right? The discontinuity is maximum at these boundaries. And as you go towards the middle portion of the waveform, it's going to be much smaller and it will be 0. So the error signal might look something like this, right? Others might be 0, right? Something like this. Okay. So this error signal is essentially a periodic signal with a period of 1024. Okay. And for the sake of simplicity and for easier understanding of what's happening here, what I will say is that this error signal can be thought of as an impulse, right? So I will say that the error is maximum only at this edge, that is only at 0, 1024, 2048, and so on, right? And the error that is getting added to the samples just to the left and right of it are very small, and we can ignore it. Okay, this is just a simplified approximation I'm making here. So the error is getting added only at these samples, 0, 1024, and 2048, and all the other samples in between are 0. Okay, so this is a simplified approximation we are making, right? And now since this is a periodic signal with a period of 1024, in the frequency domain, if you look at the spectrum, it will contain frequencies which will be multiples of the fundamental frequency, right? 2 pi by 1024 is the fundamental frequency, and it will contain only harmonics of that signal. Okay, and since the time domain signal is an impulse time, so even in the frequency domain, all these frequency points, right, they'll have the same strength. Okay, so essentially you can think like this, right? So we have an impulse train in the time domain, we get the impulse train in the frequency domain also. Okay, and as we saw here, these frequencies will be what? They will be this, right? K times 2 pi by 1024. So the first will be 0, second will be 2 pi by 1024, third will be 2 into 2 pi by 1024, and so on. Okay, and we'll have to 2 pi into 1023 by 1024, right? So now if you take a 1024 point DFT, so we'll have a total of 1024 bins, right? So starting from 0, 1 to till 1023. And you know that each bin, that is a bin K, corresponds to a frequency of this, right? So essentially what this means, when you take the 1024 point DFT, so these bins will come here, right? I mean, these impulses will just appear here, and then they will occupy all the frequency bins in the DFT, right? And because of this, when you plot the DFT, we'll have this flat portion in the spectrum. Okay. So that is why we have this flat portion here in the spectrum, right? And for the same reason, if you look at the noise shaping ADC also, where is it? It is here. So ideally what we expect is a hyper-shaped spectrum for the quantization noise like this, right? But when we truncate the signal for a total of n samples, and when we take the DFT, because of the fact that the quantization noise need not be periodic in a noise shaping ADC, when we form the periodic repetition, we will have this sudden jumps at the boundaries. And these sudden jumps will happen again periodically. And because of that, we'll have a flat portion in the spectrum. Okay, so the overall spectrum, instead of looking like a hyper-shaped spectrum like this, will be flat at low frequencies, right? And that is what we saw in the simulation as well here. Okay. And we saw that the solution to this was to use a windowing function, right? And the philosophy behind using the windowing function is the following. We observed that the discontinuities are happening only at the edges, right? So instead of giving equal weightage for all the samples, we give lesser weightage for the samples at the edges and give maximum weightage for the ones in the middle, right? And we saw hand window as one example. And what hand window does is that it splits the frequency bin to 3 neighboring bins. That is 2 neighboring bins, right? So a single bin gets spilled over to a total of 3 bins. And also, since here the samples near the edges are weighted less, we can expect that the total power in the signal after we apply windowing will be reduced, right? And for the hand window case, we saw that this factor was 3 by 8. Okay. But of course, when you try to find the signal to quantization noise ratio, this might not cause an issue, because when we are applying the window function, we'll apply to the ADC output, which contains both the signal and the quantization noise. Okay. So this reduction in the power that is happening due to the hand window will happen both for the signal as well as for the noise, right? So when you take the ratio of the two powers, there will be no change. Okay. So let's stop here.